So today we're going to be looking at conservation of energy in a system of non-conservative forces. So a non-conservative force is a force which the work done by that force in moving a particle between 2 points is different for different paths taken. So say we have point A and we have point B over here, and there's some particle here and it goes along this path. The work done is not equal to the work done if we take this path. And we remember that previously we found out for a conservative force, if the work done for moving this particle wouldn't matter, would be the same regardless of the path that we took. Examples of such forces are friction, the driving force, air resistance, when work is done by a non-conservative force, it converts energy into movement. Such as a driving force, like say in a car, will take the chemical energy of the fuel and convert that into kinetic energy. The total energy is conserved because energy is always conserved. But mechanical energy increases. When work is done against a non-conservative force, so this is an example, it would be against friction. It converts movement into other forms of energy. For example, heat when friction acts. Energy is therefore lost from the system. Although it's not actually lost, it's just converted into other forms of energy. It's lost from the mechanical system. Now, if we were to kind of move that backwards, say you were pushing a crate from one point to another and along a rough surface, there's mechanical energy is lost, and in the form of heat or noise. If you were to kind of go backwards, you can't reclaim that that mechanical energy. The energy has been dissipated into non-mechanical energy. The total energy is conserved, but the mechanical energy is lost. So let's look at a few examples of this in practice. So a ball of mass 50 grams falls from rest through a height of 80 centimeters. It rebounds to a height of 30 centimeters. Find the mechanical energy lost in the motion. So the initial kinetic energy is 0, and the final kinetic energy is 0 because it starts from rest. The ball starts from rest, it bounces down. It's got kinetic energy down here, and then it bounces back up, and at this point here again it's got no kinetic energy. So the energy is going to be lost in the form, we're going to look at the loss of gravitational potential energy. So it's going to be mgh initial minus the mgh final. So we can, that's going to be, the mass is, now first let's look at the mass is 50 grams, which is the same as 0.05 kilograms, and the height is 80 centimeters, which is 0.8 meters, and then it's 30 centimeters at the end, which is 0.3 meters. You need to make sure that everything's converted into the correct units. So we've got our 0.05 meters. We're going to take the m and g out, times 10, and then we've got the initial height, which was 0.8 minus 0.3, which will give us 0.25 joules of energy lost. And this would be converted into some heat and some sound. Let's look at another example. A crate of mass 50 kilograms slides across a rough horizontal floor. The crate has an initial speed of 3 meters per second and is brought to rest by friction. The distance travelled by the crate is 4 meters. Find the coefficient of friction. So, the motion is horizontal. Therefore, no gravitational potential energy. So we're thinking about the loss of kinetic energy. So that's going to be half the mass times the change in velocity. So it's going to be half, the mass is 50 kilograms, and the velocity, the change in velocity is 3 squared minus 0. So there is going to be a loss of 2 to 5 joules of energy. So using the work energy principle, the work done against friction must be 225 joules because there's no other forces at work here. So let's think about our crate here. So it's got our mass of, our weight is 500 newtons, and that's going to be the same as the reaction force because they're perpendicular. And we have the motion in this direction. And there's no driving force. The only thing slowing it down is friction. So friction is equal to the coefficient of friction times the reaction force. So our reaction force is 500 newtons and our friction is what we're looking for. So 500 times mu would be the force of friction. So work done by friction will be minus, because in the opposite direction to the motion, the force times the distance. So it's minus the force, which is going to be 500 mu times the distance travelled, which is 4 meters. And the work done is 225. So this gives us mu is equal to 0.1125. Now, we'll look at a couple more. A parcel of mass 3 kilograms slides down a rough slope inclined at 20 degrees to the horizontal. The coefficient of friction is 0.5 when it reaches the bottom, it has speed 8 meters per second. Use the work energy principle to find the speed at the top. So let's draw our force diagram. So we've got 20 degrees, and here is our parcel. It has weight 30 newtons, and the reaction force will be perpendicular to the slope, and we have friction parallel to slope in the opposite direction. So we'll resolve the perpendicular to slope to give us the reaction force, which must be 30 cosine 20, which is 28.2 newtons. Now we can find the frictional force, F, is going to be mu r, which is 0.5 times 28.2, which gives us 14.1 newtons. So the increase in kinetic energy plus the increase in gravitational potential energy gives us the work done. So let's first think about the increase in kinetic energy. So we're going to say the speed at the initial speed, it's right here, initial speed we'll call u meters per second, and the final speed we know as 8 meters per second. So the increase in kinetic energy is going to be half m, and it's going to be v squared minus u squared, which is going to give us half times 3 times 8 squared minus u squared, which will be 96 minus 1.5 u squared joules. I forgot to write, it slides 3.5 meters down the slope. So let's think about the height it was at the beginning. So what's this height here? So if we think about the height, and this is 20 degrees, and the length of the slope that it goes down is 3.5 meters. So h must be 3.5 times the sine of 20, which gives us 1.2 meters. Now the increase in gravitational potential energy is going to be, well, it's going to be negative because it's losing gravitational potential energy. And because at the bottom it's going to have none. It's going to be 0 because it loses that height. So it's mgh, which is minus the mass, which is 3 times 10 times 1.2, which is minus 35.9 joules. Therefore, the increase in kinetic energy plus the increase in gravitational potential energy is the work done. So we've got our 96 minus 1.5 u squared minus the 35.9, which we can work out to be 60.1, and it would be so minus 1.5 u squared joules. Now, the only force acting is going to be work done against friction, so the work done against friction is the force of friction times the distance. So the frictional force we've got up here was 14.1, and it travels 3.5 meters, so that gives us 49.3 joules. Hence, this must equal 39.3 joules. If we work all that out, we'll get an initial speed of u equals 8.54 meters per second. Now, one more problem. A car of mass 1,500 kilograms, and that includes the driver, is travelling at 64 kilometers per hour along a road. The driver sees a ball rolling out. He takes 2 seconds to react before applying the brakes using the maximum braking force. The car comes to rest. Missing the ball. After travelling a total of 80 meters from when the driver first saw the ball. So that's important, from when he first saw the ball. Assuming the wheels lock when the brakes are applied so the car slides and the air resistance can be ignored, find the coefficient of friction. So, first thing is to notice that we've got the speed as 64 kilometers per hour. So we need to change this into meters per second. So that would be 17.78 meters per second. Now, it takes him two seconds for his the brain's normal reactions to apply the brakes. So we're going to use velocity as distance over time to find the distance that he travels between seeing the ball and when he starts to put the brakes on. So that is going to be the velocity times the time, so it's 17.78 times 2, and that gives us a distance of 35.56 meters. So then he applies the brakes. So the distance travelled under braking, so when the car's kind of sliding to a halt, must be the 80 metres. Remember that he travelled a total of 80 metres from the point of seeing the ball. So that 80 metres minus this distance, the 35.56, and that's 44.44 metres. So let's think about there's no gravitational potential energy because he's on the horizontal. So it's all done, it's going to be the change in kinetic energy, the increase in kinetic energy is going to be, so half m v squared is half times the mass 1500 times the velocity 17.78 squared, and this is lost, this is going to be lost, and it's going to be, and its final speed is 0. So it would actually be, let me just add that in there. So you'd have the 0 for his final kinetic energy minus his initial kinetic energy. So it's going to be minus 237,037 joules. Now the force acting is the work done against friction. Is going to be this, the same as the change in kinetic energy. So the average frictional force, so this is work done against friction, is going to be the same as the force times the distance. And we know so this gives us the force is going to be 237,037 over the distance, which we worked out as being 44.44. So his frictional force is 5,333.33 newtons. Now, we know that F frictional force is the coefficient of friction times the reactive force. So R is the same as mg because it's perpendicular to it's opposite to the weight because the car's on the horizontal. So that will be 1500 times 10. So 15,000. So that would be, we know the friction force. So the coefficient of friction will be our friction force, which is 5,333.33 over R, which is 15,000, and that will give us 0.356. So hope that helps.